How the solar system will end, from the sun's death to Earth's fate. Part 1. The sun's life cycle from birth to death. Our sun, a seemingly eternal beacon in the sky, is a star with a finite lifespan, a cosmic journey from birth to an eventual demise. It began approximately 4.6 billion years ago, coalescing from a vast cloud of gas and dust under the relentless pull of gravity. As this protostellar material collapsed, its core grew hotter and denser, eventually reaching the critical temperature and pressure required for nuclear fusion to ignite. This pivotal moment marked its birth as a main-sequence star, a phase it currently inhabits, happily converting hydrogen into helium and radiating immense energy across the solar system. This main-sequence phase, where hydrogen fusion dominates, is the longest and most stable period in a star's life. For our sun, this era is expected to last for roughly 10 billion years in total. We are currently about halfway through this serene period, enjoying the stable output of light and heat that makes life on Earth possible. The sun is a G-type main-sequence star, often referred to as a yellow dwarf, though its size is quite substantial compared to most stars in the galaxy. Its stability is a delicate balance between the outward pressure of fusion and the inward crush of gravity. Over billions of years, the sun has been steadily burning its hydrogen fuel. While seemingly constant, this process subtly alters the sun's composition. Helium, the product of fusion, accumulates in its core, slightly increasing the core's density and temperature. This gradual change leads to a very slow but perceptible increase in the sun's luminosity over cosmic timescales. Early Earth received significantly less solar radiation than it does today, a factor crucial for understanding the planet's geological and biological evolution. As the hydrogen fuel in the core dwindles, the delicate balance that defines the main sequence phase will begin to waver. This transition marks the beginning of the end for the sun as we know it. The core, increasingly dominated by inert helium, will no longer be able to sustain fusion at the same rate, leading to gravitational contraction. This contraction will, paradoxically, cause the outer layers of the sun to expand dramatically, ushering in the next, more dramatic stage of its stellar evolution. The stage is set for a profound transformation. The ultimate fate of a star is largely determined by its initial mass. Our sun, being a star of intermediate mass, is destined to evolve into a red giant, then shed its outer layers to expose a white dwarf remnant. More massive stars meet a far more cataclysmic end, often exploding as supernovae and leaving behind neutron stars or black holes. Understanding the sun's life cycle provides a crucial astrophysical lens through which we can comprehend the destinies of countless stars across the cosmos. Part 2. The swelling into a red giant. The sun's serene main sequence phase will not last forever. In approximately 5 billion years, its core will have largely converted its hydrogen fuel into helium. With the primary fuel source depleted in the core, nuclear fusion will begin to falter, and gravity will gain the upper hand. The helium-rich core will start to contract under its own immense weight, becoming denser and hotter. This contraction, a counterintuitive precursor to expansion, will generate significant heat, causing the layers of hydrogen surrounding the core to ignite in a shell of fusion. This hydrogen shell burning will unleash a tremendous amount of energy, far exceeding the sun's current output. The intense heat and pressure from this shell will push the sun's outer layers outward, causing them to expand dramatically and cool significantly. As the surface temperature drops, the sun's color will shift from its current yellow-white to a deep, ominous red. This transformation marks the Sun's entry into its red giant phase, a truly colossal and luminous stage in its life. During this red giant phase, the Sun's diameter will swell immensely, potentially reaching beyond the current orbit of Earth. Imagine a star so vast that its surface envelops planets that once orbited it at a safe distance. The sheer scale of this expansion is difficult to comprehend. Our familiar star will become an entirely different entity, a bloated and fiery behemoth, dominating the inner solar system. This expansion will profoundly alter the environment for any remaining celestial bodies. The increased luminosity, despite the cooler surface temperature, will be staggering. The Sun will shine hundreds, possibly thousands of times brighter than it does today. This intense radiation will have devastating effects on the inner planets, searing their surfaces and evaporating any atmospheres or oceans. The sheer heat will transform their landscapes into barren, molten worlds, long before the Sun's physical expansion reaches them. Life, as we know it, will be utterly impossible. The red giant phase itself is not a permanent state. While dramatically longer than the rapid expansion, it is still a finite period. As the helium core continues to contract and heat, it will eventually reach a critical temperature and pressure, triggering a new round of fusion, helium fusion into carbon and oxygen. This new energy source will temporarily stabilize the red giant, but its ultimate fate remains to evolve further, shedding its outer layers in a spectacular display. Part 3. What happens when Earth is scorched? Long before the Sun physically expands to engulf Earth, our planet will face an inferno of unimaginable proportions. As the Sun transitions into its red giant phase, its luminosity will steadily increase, turning our familiar blue marble into an uninhabitable wasteland. This gradual but relentless escalation of solar radiation will initiate a catastrophic chain of events, rendering Earth utterly unrecognizable and hostile to all forms of life. Initially, the rising temperatures will cause Earth's oceans to evaporate, sending vast quantities of water vapor into the atmosphere. This dense, humid atmosphere will trap even more heat, creating a runaway greenhouse effect far beyond anything Earth has experienced in its geological history. The planet will become a scorching hot, Venus-like world where surface temperatures soar, and any remaining liquid water boils away into space. The once vibrant ecosystems will perish. As the Sun continues its red giant evolution, its luminosity will intensify further, transforming Earth's surface into a molten landscape. Rocks will melt, creating vast seas of lava, and the atmospheric pressure will become immense, perhaps even leading to the complete loss of its atmosphere as intense solar winds strip it away. The very crust of the planet will be utterly reshaped, its geological features erased by the extreme heat and radiation. Any signs of life, from the smallest microbes to the remnants of human civilization, will be utterly incinerated and erased. The delicate molecular structures that support life cannot withstand such extreme conditions. Earth will be reduced to a barren, glowing cinder, a stark monument to the Sun's overwhelming power and the fragility of planetary habitability. This process will unfold over millions of years, a slow-motion catastrophe. Eventually, the Sun's outward expansion will physically reach Earth's orbit. Even if Earth were to miraculously survive the scorching, the immense gravitational pull and sheer physical size of the red giant Sun would spell its doom. The planet would either be vaporized by direct contact with the Sun's outer layers, or torn apart by tidal forces, its remnants absorbed into the expanding star. The home of humanity will cease to exist. Part 4. Mercury and Venus swallowed by the Sun. Mercury, the innermost planet, will be the first celestial body to face the Sun's wrath directly as it swells into a red giant. Its orbit, already incredibly close to the Sun, will be easily engulfed by the expanding stellar envelope. The immense heat and direct contact with the Sun's outer layers will ensure Mercury's swift and complete disintegration. Its rocky material will be vaporized and absorbed into the expanding star, leaving no trace behind. Following Mercury, Venus will suffer a similar, albeit slightly delayed, fate. Its proximity to the Sun means that it too will be engulfed as the red giant continues its inexorable expansion. Venus's already scorching hot, dense atmosphere will offer no protection against the encroaching stellar inferno. The planet will be stripped bare, its silicate rocks melting and vaporizing as it becomes one with the Sun's outer layers. The process of planets being swallowed is not instantaneous but rather a gradual absorption. As the Sun's outer atmosphere expands, it will encounter these inner planets. The friction between the planet and the tenuous but extremely hot stellar material will create immense drag. This drag will cause the planets to spiral inward, accelerating their descent into the Sun's core. This inward spiral will generate additional heat, further contributing to their vaporization. This engulfment highlights the dynamic and often destructive nature of stellar evolution. What were once stable, orbiting worlds become fuel for the star that created them. The matter that formed Mercury and Venus, once distinct and organized into planetary bodies, will be reintegrated into the Sun, becoming part of its vast, hot plasma. Their individual identities as planets will be utterly erased. The disappearance of Mercury and Venus serves as a stark precursor to Earth's own inevitable destruction. Their fate provides a tangible glimpse into the future of our own planet, emphasizing the overwhelming power of stellar evolution and the transient nature of even seemingly solid celestial bodies when confronted with the dying throes of their parent star. Their end will be a violent and complete erasure. Part 5. The Fate of Mars and the Outer Planets. While Mercury, Venus, and Earth are destined to be incinerated or swallowed by the expanding red giant Sun, the fate of Mars is more ambiguous, clinging to the edge of habitability before ultimately succumbing. As the Sun swells, Mars will experience a dramatic increase in temperature, causing any residual ice at its poles and beneath its surface to melt and evaporate. Its thin atmosphere will be stripped away by the intensifying solar wind, leaving behind a barren, superheated world. The question of whether Mars will be physically engulfed by the red giant Sun remains a subject of ongoing scientific debate. Depending on the exact maximum extent of the Sun's expansion, Mars might narrowly escape direct engulfment. However, even if it avoids being swallowed, the sheer heat and radiation from the enormously expanded Sun will render it completely uninhabitable, turning its surface into a molten landscape, or at least a baked, airless rock. Further out in the solar system, the gas giants Jupiter, Saturn, Uranus, and Neptune will face a different, less immediate threat. They are far enough from the Sun that they will not be physically engulfed. However, the vastly increased luminosity of the red giant Sun will dramatically warm these distant worlds. Their frigid atmospheres will begin to heat up, potentially leading to significant atmospheric changes, evaporation of ice moons, and alteration of their internal dynamics. For planets like Jupiter and Saturn, the intense solar radiation could cause their upper atmospheres to expand and potentially escape into space, leading to a slow but significant loss of mass over cosmic timescales. Their moons, many of which harbor vast reserves of water ice, could melt, forming temporary oceans or evolving into warm, potentially even wet environments, though the conditions would still be extreme compared to early Earth. The more distant ice giants, Uranus and Neptune, along with their numerous icy moons, will experience the most profound transformation. Their surfaces, currently frozen solid, will thaw, potentially creating vast liquid water oceans under their icy crusts. This warming could lead to complex geological activity and even, speculatively, the creation of transient habitable zones around these distant worlds, though only for a temporary period in the Sun's long decline. Part 6. The Sun's collapse into a white dwarf. After the dramatic red giant phase, the Sun will undergo another profound transformation. Having exhausted its helium fuel in the core, and with insufficient mass to ignite heavier elements, the outer layers of the Sun will become unstable. Intense thermal pulsations will cause the star to shed its outer envelope, gradually expelling vast quantities of gas and dust into space. This magnificent expulsion will form what is known as a planetary nebula, a beautiful, ethereal shell of glowing gas. At the heart of this expanding nebula, the Sun's core will remain, stripped of its outer layers. This remnant core, incredibly dense and still intensely hot, will continue to contract under gravity. With no more fuel for fusion, the core will shrink dramatically, eventually reaching a stable state supported by electron degeneracy pressure. This is the birth of a white dwarf, the final evolutionary stage for stars of the Sun's mass. A white dwarf is an extraordinary object, roughly the size of Earth, yet containing approximately half the mass of our original Sun. Imagine squeezing hundreds of thousands of Earths into a single, planet-sized sphere. This extreme density means that a spoonful of white dwarf material would weigh many tons. It is an incredibly compact and luminous remnant, glowing fiercely from its residual heat rather than ongoing fusion. Over unimaginable timescales, billions and even trillions of years, this white dwarf will slowly, imperceptibly cool. Without an internal heat source, it will gradually radiate away its remaining thermal energy into the cold vacuum of space. As it cools, its luminosity will diminish and its color will shift from white to yellow, then red, eventually fading into a hypothetical black dwarf. A cold, dark, and theoretical object that no longer emits significant light or heat. The Sun's transformation into a white dwarf signifies the true end of its active stellar life. It will no longer be a life-giving star, but a dense, cooling ember, a silent testament to its once fiery existence. This compact remnant will continue to exert a gravitational pull on the remaining planets and debris in the solar system, albeit with significantly reduced influence compared to its red giant phase. Part 7. The Kuiper belt and Oort cloud drifting away. As the Sun collapses into a white dwarf, the outer reaches of the solar system will experience profound changes, but of a different nature than the fiery demise of the inner planets. The Kuiper belt, a vast ring of icy bodies beyond Neptune, and the even more distant Oort cloud, a spherical shell of comets enveloping our system, will find their gravitational ties to the Sun significantly weakened. During the red giant phase, the Sun will lose a substantial fraction of its mass, perhaps up to half of it, as it expels its outer layers to form a planetary nebula. This dramatic mass loss will have a direct and crucial impact on the gravitational forces holding the solar system together. The The gravitational pull exerted by a star is directly proportional to its mass, so a less massive sun will mean a weaker grip on its distant orbiting bodies. With a significantly reduced gravitational tether, the orbits of objects in the Kuiper belt and Oort cloud will widen considerably. Many of these icy bodies will find themselves on increasingly eccentric and unstable trajectories. Some might be flung out of the solar system entirely, becoming interstellar wanderers lost to the vast emptiness between star systems. Others might shift their orbits, potentially creating new patterns of cosmic debris. The tenuous Oort cloud, already loosely bound to the Sun, will be particularly susceptible to these changes. Its outermost members, which are only weakly gravitationally bound even today, will likely detach and drift away into the interstellar medium. The Oort cloud, once a reservoir of comets periodically entering the inner solar system, will largely dissipate, its icy inhabitants becoming lone travelers through the galaxy. This gravitational loosening means that the outer solar system will become a much emptier and less gravitationally cohesive place. The steady rain of comets from the Oort cloud, a phenomenon that has occurred for billions of years, will cease. The Kuiper belt, while perhaps retaining some of its larger objects, will also be significantly depleted, losing many of its smaller icy bodies to the cold expanse of interstellar space. The system will appear much more diffuse. Part 8. Could humanity escape the dying sun? Faced with the inevitable death of our sun, a poignant question arises. Could humanity, if it still exists in billions of years, escape this cosmic catastrophe? The answer, while scientifically challenging, is not an absolute no. The concept of interstellar travel and establishing new homes among the stars, while currently speculative, represents humanity's most plausible escape route from our dying solar system. Such an endeavor would require technological advancements far beyond our current capabilities. We would need to develop propulsion systems capable of accelerating spacecraft to a significant fraction of the speed of light, enabling journeys to other star systems within reasonable timescales. The distances between stars are immense, and even the closest exoplanets suitable for colonization are light-years away. Furthermore, finding a truly habitable exoplanet, a second Earth, would be a monumental task. While thousands of exoplanets have been discovered, identifying one with the right conditions, liquid water, a stable atmosphere, appropriate temperature, and a benign host star is incredibly difficult. Even if such a planet is found, terraforming it or adapting to its unique environment would pose immense engineering and biological challenges. Alternatively, humanity might choose to establish colonies on space habitats or terraformed moons within our own solar system, perhaps in the outer regions less affected by the red giant sun. However, such colonies would still be temporary solutions, as the sun's eventual white dwarf stage would mean a drastic reduction in energy and warmth, necessitating highly advanced artificial environments to sustain life. The concept of star lifting, where advanced civilizations could manipulate stars to extend their lifespans or even move entire star systems, is a fascinating but purely theoretical possibility. This level of cosmic engineering is so far beyond our current understanding that it remains firmly in the realm of science fiction. For now, interstellar migration remains the most tangible, if distant, hope. Part 9. The solar system in billions of years. Billions of years from now, the solar system will be an unrecognizable landscape, a pale shadow of its current vibrant form. The once bright, life-giving sun will have transformed into a faint, cooling white dwarf, no larger than Earth. The inner planets, Mercury, Venus, and Earth, will be gone, vaporized or absorbed by the red giant sun. Their material will be mixed within the white dwarf's dense core, a silent testament to their fiery demise. Mars, if it escaped direct engulfment, will be a barren, airless cinder, its surface baked and sterilized by the Sun's earlier red giant phase. The gas giants, Jupiter, Saturn, Uranus, and Neptune, will still exist, orbiting the distant white dwarf, but their environments will be profoundly altered. Their atmospheres might be thinner, and their icy moons, once warmed by the red giant sun, will have refrozen, becoming once again desolate and frigid worlds. The Kuiper belt and Oort cloud, once vast reservoirs of icy bodies, will be significantly depleted. Many of their objects will have drifted away into interstellar space due to the Sun's mass loss during its red giant phase. The gravitational architecture of the outer solar system will be much looser, and the frequency of cometary visitors to the inner regions will have dramatically decreased. Over truly immense timescales, the white dwarf sun will slowly cool, gradually fading into obscurity. It will become less and less luminous, eventually turning into a cold, dark, black dwarf, an entirely theoretical object that no longer emits light or heat. At this point, the solar system will be plunged into perpetual darkness, illuminated only by the faint glow of distant stars. Eventually, even the orbits of the remaining planets around the black dwarf could be disrupted. Over trillions of years, gravitational perturbations from passing stars or rogue planets could slowly nudge the surviving planets out of their orbits, flinging them into the cold, empty expanse of interstellar space. The solar system, once a bustling cosmic neighborhood, will eventually disperse, its components scattered across the galaxy. Part 10. What the end of our system tells us about the universe. The inevitable demise of our solar system, from the Sun's red giant phase to its final collapse into a white dwarf and the eventual scattering of its planetary remnants, is not an isolated incident, but a universal narrative. Our solar system's fate is a microcosm of the life cycles playing out across the cosmos, a powerful illustration of stellar evolution and the transient nature of even seemingly stable celestial structures. By understanding the future of our Sun, we gain profound insights into the destinies of countless other stars and planetary systems throughout the galaxy. The vast majority of stars in the universe are low to intermediate mass like our Sun, and they are all destined to undergo similar evolutionary paths, swelling into red giants before ending their lives as white dwarfs. This predictable cycle underscores a fundamental law of astrophysics. The observation of planetary nebulae, the beautiful glowing shells of gas expelled by dying stars, provides direct evidence of this process occurring elsewhere. These cosmic artworks are the nascent stages of white dwarfs, offering us a glimpse into our own Sun's future. Similarly, the discovery of white dwarfs with orbiting planetary remnants further validates our understanding of these stellar end states. The study of exoplanets around aging stars also informs our predictions. Astronomers are actively searching for and studying planets orbiting red giants and white dwarfs, trying to understand how planetary systems adapt, or fail to adapt, to the dramatic changes in their host stars. These observations help refine our models of planetary survival and destruction. Ultimately, the end of our solar system is a testament to the dynamic and ever-changing nature of the universe. It reminds us that everything, from stars to galaxies, has a beginning, an evolution, and an end. This cosmic dance of birth, life, and death is what shapes the universe, recycles matter, and ultimately provides the raw materials for new generations of stars and, perhaps, new opportunities for life elsewhere.